Hello, and welcome to one of the CLIPC guidance videos. By means of our use cases, we aim to demonstrate which kind of analyses you can perform using the various CLIPC tools. This use case deals with the assessment of climate change impacts on heat stress, for which the CLIPC platform is used to model the impacts. Imagine the following scenario. A group of EU decision-makers ask an impact researcher to identify the most vulnerable regions in the Iberian Peninsula via a Heat Vulnerability Index, or for short, HVI. The researcher develops the HVI to account for three aspects, namely future temperatures across the Iberian Peninsula, future urban area, and past adaptation of the population to the current climate. She breaks her analysis into two steps. First, she needs to determine indicators of changes in temperature and urban area in Europe, as well as the current adaptability of population to heat stress. Second, she needs to combine the results of Step 1 to produce a Heat Vulnerability Index map for the Iberian Peninsula. So let's begin with the analysis by accessing the CLIPC combine function.
Don't forget to log in because otherwise you will not be able to save your results.
First, we want to assess the change of summer days in Europe. To do this, we select the theme Temperature, the indicator Summer Days, and the dataset JERICS Multi-Model RCP 8.5. For the time period, we select 2031 to 2050. On the right-hand side, we also select the theme Temperature, the indicator Summer Days, and the dataset JERICS Multi-Model Historical. For this indicator, we chose 1981 to 2000. Both indicators receive equal weight. We choose None as the normalization, then select Subtract as the processing operator, and name our output SU change, and then click Execute. The result can now be used for the next step. For the next step, load the newly computed indicator into the indicator selection to the left. Select My Data and then the file ending with SU change. On the right-hand side, select the theme Settlements, the indicator Area of Urban, Mainly Residential Land, and select Dataset IRPUD JRC Louisa. For this indicator, select the time period 2031 to 2050. As the measurement scale of both indicators differs, we need to normalize the indicator values. Therefore, we select min-max as the normalization and multiply for processing. We do this so that the highest increase of summer days and the densest urban land get the highest score. Name your output file, for instance SU-URB, and click on Execute. Our result can now be employed for the last analytical step. For the last step, load our newly created indicator into the indicator selection to the left-hand side. Go to My Data and select the file that ends with SU-URB. On the right-hand side, we will choose the theme Settlements, the indicator Minimum Mortality Temperature, and the dataset PIK Multi-Mixed, this one here. Again, choose min-max as the normalization method, subtract as the processing method, and give your output a name. Let's name it HVI, and hit Execute. Our result now shows us the vulnerability to heat stress. Regions are less vulnerable that show negative values or values close to zero. In contrast, positive values represent higher vulnerability. When zooming in to the Iberian Peninsula, you can see that particularly the big cities are depicted as vulnerable towards heat stress, which appears logical. Going back to the theme of our use case, this result could be used by a researcher for further analyses. If you want to learn more about the CLIPC tools, use the help function you find throughout the toolkit, or watch our other guidance videos.